Hello everyone, and welcome to my talk about mixing latency jobs and throughput jobs in the same application using application level priority management. So a little bit about me. I won't read to you the slides. I'll just let you absorb it. So let's start by comparing throughput-oriented jobs and latency-oriented jobs. So throughput computing, it's often called online analytics processing. The goal here is to reduce the total time of an operation, of a large operation. And for that, we want to increase utilization. We want to make sure that every cycle that the machine has to offer is spent during our computation. Usually, we do extensive buffering to hide device latency or network latency, read ahead and write behind. And this allows us to increase utilization. And we have a small number, sometimes just one, sometimes more, of macro operations, and serialization is permissible. We don't care if one operation completes before the other starts, so long as the total time of all of the operation is low. In contrast, with latency computing, often called online transaction processing, we have to leave free cycles to absorb bursts. If we're running at 100% utilization, then and there is a surge of traffic, then we will have stalls and we won't be able to serve everything with reasonable latency. We cannot do buffering because it's hard to predict which data we will need to read. Of course, caching works, but we often do have to wait for data to arrive from disk or from the network. And often we must write synchronously to disk in order to ensure that the data is committed. The time of each individual operation is critical. There is often a user that is waiting on the other end. And so we need to make sure that all of the operations complete with low latency. Many of the operations have to execute concurrently. So this is because we might be waiting on disk, and if we serialize operations, then we end up adding up all of the latency of individual operations, whereas if we execute them in parallel, we can overlap those delays. So you can see they're very different from each other. So the question first has to be asked, why even bother mixing throughput-oriented jobs and latency-oriented jobs? So one answer is you want to run those different workloads on the same data. You have a database that is serving users, but you also want to run analytics on all of the data. And you can do that by splitting the data by duplicating the data on multiple clusters, one for each job, but that is wasteful of resources. And it's better, if you can, to run those two jobs on one cluster and share the resources. And another case, which might be more common these days, is that when you have an OLTP workload that has an internal throughput-oriented job that is required in order to maintain it. A typical example is garbage collection, where you have the memory management system running over all of the memory and weeding out memory that is no longer needed and compacting the other memory. More complicated examples are grooming a log structure merge tree. This is running compaction jobs in order to merge duplicate files and reduce the number of files that are needed to serve reads. And also cluster maintenance, where you're adding nodes or removing nodes, backing them up, rebuilding them. So all of these operations, you want them to complete quickly, but you're not interested in the latency of individual bits. You're interested in getting the total time to do the job to finish as quickly as possible. So what's the general plan? How are we going to approach this job? So first, we'll isolate the different tasks. so different tasks for latency jobs and for throughput jobs, so that we can measure and control them. And then we're going to schedule them in some way that allows the latency jobs to complete quickly and doesn't allow the throughput-oriented jobs to interfere with them. So a traditional way of isolating tasks is to run each task in a thread. And people quickly found out that creating threads is slow, so they used thread pools, and each task borrowed a thread from the thread pool, used it, and then returned it to the pool, and then let the kernel schedule all of these threads. The kernel has a thread scheduler, and we can influence the way the kernel chooses which thread to run with priorities. So we might give a high priority to our latency-sensitive jobs and a low priority to our throughput-oriented jobs. So what are the advantages and disadvantages of this approach? And just from the length of the list, you can probably see in which way I'm biased. So the advantages is that it's well understood and that there's a large ecosystem that's dedicated to it. It's simply the traditional way of doing things. And this is really a huge advantage because it means you will have to do less work yourself and you will have fewer surprises. But there are also disadvantages for the more demanding applications. So first, context switches are expensive. If your tasks are really small, then the context switches start dominating the cost. Communicating priority to the operating system is hard. The priority levels are not very meaningful, and it's a game of hit and miss. When you have many threads, then locking becomes complicated and expensive. And there's a chance of priority inversion, where a lock that's held by a low priority thread becomes important for a high priority thread, which needs to wait for it. And then it sort of inherits the priority of the low priority thread. And finally, the kernel scheduling granularity might not suit your application. You can try to tune it, but there's a limit to what you can achieve with that. So the different approach, and the approach that we use with C-Star and ScyllaDB, is application-level task isolation. So in this approach, every operation is a normal object. It's an active object with a virtual function that's called when it needs to run. And those tasks are multiplexed on a small number of threads, and ideally just one thread per logical core. And why one thread per core? If you have fewer, then of course you're going to leave some cores idle. And our goal was to have all threads busy, all cores busy at all times. And if you have more threads than you have cores, then you're back letting the kernel choose which threads to execute. And our goal here was to do the scheduling ourselves. And because of that, you will have to run both throughput tasks and latency-sensitive tasks on the same thread, and you will have to juggle between them. And we will have a concurrency framework that assigns the tasks to threads and controls in which order those tasks are executed. And this is really the key to the whole thing, how to pick which task to execute next. So let's look at the advantages and disadvantages. So the first advantage is that you have full control over everything. So you can fine-tune everything to your heart's content in order to get the best possible results. I also listed it as a disadvantage because you can also spend too much time doing this fine-tuning and not paying attention to your application. So it's a double-edged sword. You can get very low overhead with cooperative scheduling. So the locking becomes simpler. Some of the locks just go away and the others become less expensive. You have good CPU affinity, so the tasks remain on the same CPU, tasks that access related data, and this is very good for CPU efficiency. And because the kernel is making fewer decisions, you will get fewer surprises from the kernel. And as I mentioned, one of the disadvantages is that you have too much control and you might be tempted to use it. And the ecosystem is much less mature. It's now becoming better with Rust Tokyo and Glomio, and with C++ coroutines. So it's becoming easier to use, but it's still a road that's less traveled. So this is how it looks. We have the scheduler. This is a picture of just one thread, and the other threads in the system will be identical. And the scheduler is managing a bunch of task queues, and each task queue has a bunch of tasks queued on this task queue and waiting to be executed. They might be latency-sensitive tasks, which are usually small and numerous, or they might be throughput-oriented tasks, which are usually long-running, and we would usually have a smaller number of them. So this is how the execution timeline looks. The scheduler picks a task queue and execute tasks coming from the task queue until either the task queue is exhausted or until we have a preemption, or time slice is exhausted and we need to switch to another task queue. The scheduler keeps making those decisions which task queue to switch to every time we have this boundary between queues, either due to time slice or due to running out of tasks. So what do we do when we have this boundary between queues? So first we poll for I/O. Those tasks are usually compute tasks, and we also need to make sure that we check for new I/O, new tasks to perform. So this is the way that tasks are introduced into the system. And in modern systems, this is done with I/O during enter, or the equivalent with Linux I/O. And it's very suitable because for this kind of system, because it is a batch interface. So you collect all of the I/O from the previous task that you have, and you issue it in one system call. So this is extremely efficient. And the next step is to make a scheduling decision. And the way to do that is to have some kind of metric that tells you when the system is balanced. And in our system, the metric is that the quotient of the queue runtime divided by its shares is equal across queues. So a queue that has a large number of shares, and which means it has a high share of the system resources, will have a higher runtime, and a queue that has a small number of shares will also receive a small runtime from the scheduler. And the scheduler just picks the queue that has the smallest such quotient and schedules this one for execution. That implies that the selection is not round robin. If you have a queue with a large number of shares, it might get run multiple times, one after the other. I mentioned the preemption. So in a thread-based system, preemption is easy. You don't need to do anything. The kernel will just pick a thread, put it to sleep, and execute another thread in its place. But when you have just one thread per core, you need to do the preemption yourselves. So the simple but expensive technique is to just read the clock each time you have a possible preemption point, compare it to the deadline, and if so, then give up your control of the core. But as I said, it's quite expensive. Reading a clock is a slow operation. Another way is to use a timer with a signal. So set a timer for the end of the deadline, have it send a signal, and in that signal, set a memory location, which you can check in your tasks. This works, but it's a little bit icky. It doesn't scale very well due to how signals are implemented in the kernel. And the way that we use is we have a kernel timer that writes directly to a user memory location. And the way to achieve this trick is to make the timer an entry in a Linux I/O completion queue, or I/O during, its equivalent. Because the completion needs to update the tail pointer, we can monitor the head pointer. We can monitor the head pointer for changes, and when it changes, we know that we need to preempt. It's a little bit tricky, but it's very efficient, and this is the technique we use. And last, it's important to have a stall detector. So you might forget to check for preemption in some long-running tasks, or you might not know that they're long-running. So we have a signal-based mechanism that fires whenever a task takes too long, and it generates a stack trace, which you can analyze and see where you have forgotten to have a preemption check. It's a little bit after the fact, but it's better than not having it at all. Let's look at how this is implemented in ScyllaDB. So a little bit about ScyllaDB for those who don't know. It's a distributed NoSQL database. It's oriented at latency-sensitive workloads, but it also supports analytics processing, and it also has internal throughput-oriented jobs. So it's using a log-structured merge tree. So we have a compaction job that's running in parallel with all of those user reads and writes. And also, it's a clustered system. So if we grow the cluster, we need to stream data to the new node or receive data from a node that's being decommissioned. And these are throughput-oriented jobs, since we're not interested in the time it takes for an individual record to move. We're interested in the total time to perform the operation. So this is how our queues are disposed. We have the commit log and query queues, and these are the user-facing latency-sensitive queues. The query queue is used to serve reads, and the commit log queue is used to serve writes. And the other three queues are for throughput-oriented jobs. Compaction is used to manage the log-structured merge tree. So it reads files, merges them together, and then deletes the old files. And the memtable queue is used for flushing memtables to disks, to the disk. And this is quite important because if memory fills up, then you have to block writes. So we have to make sure that the rate at which we are able to write memory, to flush memory to disk, that rate is sufficiently fast to keep up with the incoming write rate. And in a second, I'll talk about it. And there is the repair queue, which is used for cluster management. So adding nodes, removing nodes, and reconciling data between nodes. Our priorities are not just statically allocated, they're dynamically changed. If we see that our compaction job is falling behind and it's not keeping up with the rate at which data is generated, then we notice this via a backlog monitor. And the backlog monitor applies a calculation to change the priority, and that feeds back into the scheduler. And the same thing happens with the memtable. We monitor the rate at which memory is flushed to disk. If that rate is not sufficient to keep up with the incoming write rate, then we will increase the shares of that queue in order to take away bandwidth from user writes and give that bandwidth to the background job that keeps everything in order. And this makes sure that the operation is smooth and there are no hiccups. We also extended this to allow the user to control it. And we call this workload prioritization, and it allows the user to run 2 different workloads on or even more on the same cluster. And the user is able to control the shares of each queue. And there is a mechanism that, and the key for that is the login name. So you log into the database with some role name, and that role name is associated with the priority of the job. And this way you can have a microservices-based system with each microservice having a different quality of service, or perhaps you're running an analytics job concurrently with your online job, and with the shares adjustment, you can make sure that the analytics job does not interfere with your online job. And this is using exactly the same system for a different purpose. Finally, there is I/O scheduling. Logically, it's the same thing. So you're trying to mix latency-sensitive and throughput-oriented jobs on the same disk, but it's a lot more complicated. The device that you're scheduling, an SSD, is much more complicated than a CPU core. You also need to have cross-core coordination because usually you have fewer disks than you have cores. And you can learn much more about that in my colleague Pavel's talk about I/O scheduling. I highly recommend that talk. So that's it. Thank you very much, and I'll be happy to answer questions.